So my name's Edwin Faier. I'm the president and director of business development for Xiphos. I'll first give a little background on Xiphos and our products. This is going to bring the level, in terms of the level of granularity, right down to the actual processing boards and some of the low-level functions that you can do, because that's what Xiphos does. So we've been doing this since 1996. I call us the grandfathers of new space. The idea was to use terrestrial computing products and network communication and bring them up into harsh environments. Of course, it's difficult to get much harsher than space. So effectively what we do is we use industrial grade products, components in a fault-tolerant architecture, and we use them. Our architecture allows you to use these in a space environment, obviously at a much smaller fraction of the cost of a space-grade solution. So our products are basically processor boards, and FPGAs have been given a lot of press in this last hour, and I'll do the same. So our products are based on multiprocessor system on a chip FPGAs, and they're generic computing modules that would be used in a subsystem, target applications, or target markets, obviously satellites, and increasingly unmanned vehicles and science experiments on the moon. So I'll just briefly go over just a few of the key products, and then just to provide context to the rest of the slide in terms of data processing. But one of our products is the Q7. So it is based on a Zinc 7020 FPGA. So this is similar to what was mentioned by Sultan. This is a dual core ARM processor. We have some other supervisory functions on board, et cetera, to make this a space product. It's got everything you need to have a processor, but we also leverage the FPGAs. Effectively, this is a very small board, about a business card size board, weighing about 24 grams. And effectively what we do is we take most of the IO from that Zinc FPGA, and we bring it out to what's called a mezzanine connector on the bottom side of the board. So they could be used with an application-specific daughter board that is typically customized to the application. Another product that we have, this is based on the UltraScale Plus, which was also mentioned in this webinar. So the UltraScale Plus, the reason why it's so interesting is that it's got effectively 7 processors on board. It's got 4 application processors, 2 real-time processors, and a GPU, and it has about 5 times the FPGA logic as the Q7. So this is probably for very, very higher compute requirements. This is an excellent product, and it's seen its way into Earth observation systems, SAR systems, software-defined radio systems, and so on. A closed variant of the Q8 is the QHA. This is similar to the Q8, except we brought out some additional gigabit per second interfaces, mostly for software-defined radio applications. Now, a typical project or a subsystem would include the processor, which you see on the left, and that would be installed on a daughter board, which would have the specific IO, the specific connectors, form factor, functionality that would be required for a mission. Every mission is different. Some missions might require mass memory on board, like a solid state drive or so on, and different interfaces, different connector types for all applications, so that the daughter boards are typically custom. But it leverages the IO and the FPGA space and the CPU that are built into the processor boards. So to do a little deep dive, everyone talked about FPGAs and so on. So what makes them so interesting and so useful for advanced data processing? So on the left, you have the Zinc 7020. On the right, you have the UltraScale Plus. Effectively, what's important here is the fact that you have the embedded processor cores, 2 in the case of like I said, the Zinc, and up to 7, 4 application processors in the UltraScale Plus, where you would typically run your operating system like Linux and so on, as well as all standard peripherals that you would require to build a CPU around your FPGA. And then the important part, of course, is the programmable logic with built-in memory and with all the logic gates and flip-flops and so on that are part of the subsystem. And of course, these subsystems also have embedded hard cores for communications, for gigabit Ethernet interfaces, USB, CAN, and so on. So that functionality can also be brought out into the subsystem. So, I mean, it's been touched on, but just to kind of repeat it. So, why do you need the advanced data processing? So today, we need increasingly complex algorithms. Increasingly complex algorithms on smaller platforms requiring low power, low space, and with constrained power, of course. So today we have very high resolution sensors. We have software. I'm fighting PowerPoint. Excuse me. High resolution sensors and so on. So the ability to take that data and feed it to a processor. You have to do some pre-processing, and that's where the FPGA comes in. So not only do you have to interface to that FPGA, to the sensors, but you have to be able to pre-process the data so that it can be handled by the CPU itself. And modern sensors today generate gigabits per second of data, so it's impossible for processors to keep up. So you need that logic. Another application is software-defined radios, where you're not talking about data processing per se, but you are actually processing very high speed digitized RF, in gigabits per second. So you need that FPGA front end to do the pre-processing. So some examples of where this is used. So like I said, interfacing with the sensors, typically in a Earth observation, for example, type application. It looks like my presentation has a mind of its own. There's various interfaces to the cameras. These would include camera link, space wire, LVDS, or gigabit per second transceivers. Then you need real-time processing that has to be performed in the logic of the FPGA before the data is processed, is provided to the CPU. So this allows us to use a standard non-real-time Linux OS combined with the real-time front end that's happening in the FPGA in order to do this real-time application. So some examples of pre-processing that we have done, or data processing that we have done. Is so first at the very front end, you have to correct the imager. So that'll include some gain and offset adjustment, maybe some lens distortion and correction of the image itself from the camera. You might have bad pixels, and you don't want those bad pixels because you're going to be doing processing on the data. You don't want those bad pixels to infiltrate your data and reduce the quality of the data. So you have to correct for those. Binning is a very common function where you're effectively reducing the data sets by factors of 4 or 8, reducing 8 pixels into 1 it reduces the resolution, but allows you to process it in real time. Co-adding is a function where you'll add multiple images together to reduce the signal to noise. Same with TDI. Centroiding, we've done, for example, you have an image that you're looking for the center point of the image. We've done applications where we've been able to centroid at 30,000 frames per second using the logic. Feature detection, a very important thing for rovers and so on. And of course, compression. And for software-defined radios, we have all of the DSP building blocks that are required to interface to the RF transceivers at the front end, the ADCs and DACs. So I just want to talk a little bit about hybridization. So hybridization, it leverages the tight coupling of processors and logic in an FPGA, in an MPSoC FPGA. So it allows you. So logic itself excels in computing things in high volumes, like it was described by Zoltan, where you have a lot of similar calculations all going on at the same time. CPUs, of course, are good at other things. So when hybridization allows you to take a Q card and exploit those on an FPGA. So we've developed a methodology where we take conventional C code, we're able to profile that C code and see where the processor is actually spending a lot of its time, and then identifying those pieces that are amenable to be ported to an FPGA, and then we will implement that in VHDL. Then that VHDL code is the software is updated to access the VHDL code as opposed to the software library or the software function, and then you end up with an accelerated application. So as an example, so the top part of the chart shows what CPUs are good for. They do one operation at a time. So for example, if you have 3 operations, after the 4th cycle, you'll have your output. Whereas in the FPGA, you can load that pipeline with data every single clock cycle. So instead of having one result after the pipeline is filled, instead of having one result every 4 clock cycles, you'll have a result every clock cycle. So that's just an example of pipelining and how it can be improved in an FPGA. Now, if that works well, then what works even better is if you then expand that, and then so now you're able to process multiple data streams at the same time, and that is the advantage of hybridization. So what we've done is we've taken various algorithms that, for example, the Canadian Space Agency, our agency in Canada, had particular interest in a variety of particular algorithms. And what we did is we hybridized those algorithms and we compared it to their operation on the typical development environment, which is, you develop your algorithms on a PC, running, on an i7 PC, and you test out your algorithm. But then the problem is, okay, how do you get that running on a space processor that's running at 2 watts as opposed to my 100 watts Intel i7? So we've hybridized these as examples, these various algorithms, and you can see their performance. So if you look at the first column, that shows the performance versus an i7 running at 3.46 gigahertz, running multiple hundreds of watts, versus running on a 2 watt Q7. So, which is obviously very applicable for either satellite or rover applications. So you can see that in general, I mean, it depends on the application, depends on the algorithm itself. Some are more amenable to the advantages of hybridization than others. But you can see that in general, performance can either the real-time performance can either be met with a 2 watt processor, or in some cases even multiples. And of course, the big savings is on power. So if you look at the third column, that would show you the power savings and when running on a 2 watt processor versus like the i7. And effectively, it makes the difference between a mission being able to happen or not. To give another example, this is a product that we have, a system we've developed called Evo. So it uses hybridization of various algorithms. So it performs what's called visual odometry. So you're on the moon, there's obviously no GPS. You have to be able to know where you're going and keep track of where you're going. So that's what that's what visual odometry is. So it acts as a sensor that gets connected to the rest of the GNC of the rover to do localization, to tell the rover where it is. So what you see on the right, so it's basically a stereo camera which is connected to a Q7 through a board called a camera board, and we ran it through its paces. The Canadian Space Agency ran through its paces, and what you see in that graph, you see a chart of the ground truth, which is basically a GPS measurement of localization through a specific route, and what you see in green is the results from Evo. so what you have here, like something typically, again, which would run on a laptop that's sitting on top of the rover in the case of a terrestrial application, now is able to run in real time. This was actually operating at 11 hertz, able to operate in real time to be able to help the localization. We also did some other interesting things with this, with Evo. So that little video you see on the bottom right is actually our hazard detection and avoidance algorithms that are running. So because we're using stereo, we're able to localize if there's a hazard, and it's put into the GNC to actually stop the rover before it does itself some harm. It was tested with various types of obstacles. And we've also done, it runs an algorithm as well to do disparity mapping in 3D point clouds. So you can actually get a 3D point cloud when for example, when the rover's at rest, you can get a 3D point cloud to be able to plan the science. The whole idea for Evo is to get better localization and to support more autonomy, because the more autonomy a rover has, the more science the scientists can do. So as you can see, the average error was about 1%, and again, this is on this was using the Q7. The performance would even be better on the Q8, and we did testing with the rover at 6 kilometers an hour, even though we actually tested up to 10 and 15 kilometers an hour. Now, there's not going to be too many rovers taking a joyride on the moon. So, 6 kilometers an hour is certainly much more than needed. Now, just to touch on other elements, there's been a lot of talk about AI. Now, we're not an AI company, so but what we want to do is enable our customers to use AI in their platform. So we've ported Vitis AI, which was mentioned by Zoltan, to the Q8. So Vitis AI supports, various frameworks like TensorFlow and Caffe and so on, and it provides the unified software platform, provides the various elements that are required to develop an AI application and get it running on for example, the UltraScale Plus. What's interesting about Vitis, it uses something called a DPU, which is a deep learning processing unit. Effectively, these DPUs are instantiated into the logic, and they act as an artificial intelligence co-processor to the application processors in the UltraScale Plus. So the compiled data, this DPU has shared access to the DRAM on the board, along with the host CPU, and then together, so this coprocessor will run the compiled code that is generated by the Vitis toolset within the DPU. So again, it acts as an AI coprocessor. Just as an example, because again, we don't develop our own AI applications, but we have a company, one of our partner companies out in Ottawa, but a couple of hours away from us, and they're developing some very interesting algorithms using AI, and this is running either on the Q7 or the Q8. So here's just an example. So effectively, what they're doing is they're doing terrain classification. So in real time, the ability to use generally could be the navigation cameras, could be a hyperspectral camera, whatever type of cameras on board the rover, to identify and classify terrain. So what you see on for example, if you look on the bottom, the picture on the left is the image from the cameras, but what you see on the right is a real-time overlay that it used AI to identify the terrain. And so, for example, whether it's regolith, whether it's a crater, the interior of a crater, exterior, and it's color-coded for the ease for the operator. And the intent here, just like, I guess, Evo, is to accelerate the science. Another thing that it performs is something called novelty detection. So, you expect regolith, you expect a crater, you expect a boulder, but you may not expect, a small meteorite that's in the frame. So the novelty detector will provide that information to the scientists. And so again, to more quickly decide on the science that they want to do. anyway, so they use various networks, various algorithms for this, which are indicated here. So they're going to be running this. This is actually going to be flying on a mission shortly, the Emiratis lunar mission on their rover on a Q7. So again, on that 2-watt processor. And as well, they're doing work with our Q8 processor in Iceland right now, and in their own indoor, they have their own moonscape in their office building, which is always fun. And for the Q8. Now for them, Vitis AI wasn't enough because they wanted it to be a little more hardware and platform and processor agnostic. So they developed their own tool chain for this to make it a little more generic based on this the NNEF format. I'm certainly not an expert at this, but please, if you're interested in any information either about getting AI algorithms implemented on a space platform, a low power space platform, please reach out to Mission Control. I have Mikhail's contacts at the bottom of the screen, either for if you need support with AI algorithms or to access their toolchain. So just in conclusion, besides realizing that I lost the battle against PowerPoint, in conclusion, so hybrid processing, the hybrid processing that you can do in an FPGA, in a multiprocessor system FPGA, can be leveraged to perform advanced data processing. So in the case of the Q7, it's the Zinc 7020. In the case of the Q8, it's the UltraScale Plus. Generally, the real-time processing is performed in the logic before the data is provided to the CPU. So that allows you to use standard non-real-time operating systems that eases development and your development costs. You could use tools like hybridization to actually get very complex algorithms running in real time on the processor. And again, inference can be done very quickly and cheaply on an FPGA. So to get AI applications running, so whether it be through Vitis AI, through custom tool chains from third parties. That's it. Thank you very much. Thanks for the opportunity. I apologize for my battle with PowerPoint, but thank you for your time, everybody.